I might even turn on the projector this time. Here are sort of three announcements. Two of them are kind of time sensitive. The first one, and I think all of you are math or pre-engineering majors, right? Okay. Now, I was supposed to have done this a while before, but I missed seeing the email because the first of the term was just so crazy. Miss Lawson's state coronation is coming up sometime or another. I don't know when. I don't even know. I'm pretty sure you haven't voted on her yet, but whatever. But what they like to have is representatives from each department to be in her court. Okay, so if any of you are interested in being in Miss Lawson State's court, you certainly can. I encourage you to let me know today so I can nominate you if you're interested, or any of you interested. Oh, wow. Okay. I was expecting all of you to come flooding into that. Okay, so that's done. Next. And by the way, while we're on that one, I can't give you the exact time. Are you participating with Math Team this time?
No, I've been working too much.
Okay. Is anyone participating with Math Team right now? They're meeting every week for practice. I don't know their times. I know I've seen the email, but I just don't remember what it is. If you're interested, it is a great thing to do. Did you feel like you learned math last time doing it?
Yeah.
Big time. You know, so it's a fun time, and you learn to apply math and do math, and it actually helps. I think it helps you in your courses. I don't know if you felt that or not. So please, if you're interested, contact Ms. Nyla Gerasi. It's NJARAYSI at lawsonstate.edu, and let her know of your interest. Okay. That one I just happened to think while we're doing it. The second one that's really time sensitive is this one. I guess that every year they have to test the fire alarm system on both campuses, in every building on both campuses. They're in the process of doing that now. Supposedly they did some last Thursday. I never heard it, okay? But evidently they're doing just segments of the building. I never heard it. And they did other buildings last Thursday. So they may still be doing this today, tomorrow, and or Wednesday. I think they're scheduled to be through by Wednesday. So if you hear the alarm go off today and you don't smell smoke and you don't hear anyone saying, this is not a drill, this is for real, this type of thing, then ignore it. This is the only time we'll ever tell you to ignore a fire alarm drill, but they are testing the system today, tomorrow, and Wednesday. And they did a few last week, too. So they may have even done some on Friday, but I was on Birmingham campus Friday, so if they got them all tested, it may be that we won't hear any at all. But if you do, ignore it. It's not a drill. It's not a fire, real fire. It's just testing the alarm system, unless someone comes on and lets you know this is for real. Okay. So there's that. Oh, yeah. Next week is Cougar Connection Week, and I'm not going into all the details, but just let you know it's coming up. There'll be programs or events going on both campuses, Monday, Tuesday, and Wednesday, okay? And Thursday there'll be stuff mostly on the Birmingham campus, but you're welcome to participate there. They may or may not have a blood drive associated with it. I know they were talking about that. But there's lots of good information. There will be people on campus from all kinds of organizations that you can volunteer for. There will be representatives from various campus organizations if you want to be a part of those, like the Math Team or other things. So watch out for that all next week. I'll give you more details on Wednesday. You'll see signs all over the place, so read the signs. Okay, beat me to it. All right, any question on anything from here? This leads me to ask you a question, okay? If I'm remembering right, do we start in 4.2 or 4.3? 4.2 is what I was remembering too. Say that one more time. What's that?
We were saying that we
almost done with 4.4.
Yeah.
We started 4.2, but we're almost done with 4.9. We have one question left.
Yeah, exactly. Right, okay. I know that. Here's what my question was to you, though. There's one more section after this, a very important one, that's 4.5. Okay, so we did 4.2, 3, 4, and 5. We will have done. Okay. Now that seems like a lot to mix in with the next chapter and put on the test. Do you want a test on just what we've done so far in chapter 4? It's not coming up immediately, but that's what I'm asking. I need to start scheduling my time to get that test made out. Do you want one on just those 4 sections in chapter 4? Okay, that'll be one more test and probably was listed in the syllabus, but I hope you're okay with that. Okay, all right. So I wanted to know that before I forgot to ask you again. All right, so we were on, we had started example 10. We had done 10A, but we had not done 10B. Okay? And this was our figure, and here is 10B. The question was, velocity in feet per second of a particle moving along a line is v of t is equal to t cubed minus 10t squared plus 29t minus 20, where t is the time in seconds. The A part says what is the displacement of the particle on the interval t going from 1 to 5. And you did that, and basically your displacement was the integral from 1 to 5 of that function, v of t. Okay? Just that. That took into account the times you were going in a positive direction and the short time you're going in a negative direction. It all took care of that. The second one, though, the B question, what is the total distance traveled by the particle on the time interval 1 to 5? Okay? Now here's the difference here. Displacement, you are going in the forward direction because this is positive velocity from time t equal 1 all the way. Going pretty fast up here too. 6, whatever they are, feet per second, meters per second, whatever they are. Going pretty fast here, slowed down, stopped, it went to 0, and then for the next second, you move backwards a little bit. And your integration added this, subtracted that, and that gave you where you wound up. Okay, position at time t equal 5. That encountered it going here. But the second one, the total distance traveled, you traveled this distance here, but even when you stopped here and then backed up, you were still traveling some distance. Okay? So what you have to do here then is exactly what they say here. To find the total distance traveled, you calculate the integral from t equal 1 to 5, v, absolute value v of t, dt. Okay? Now, they sort of cheat on you here. They give you way too much information, I think. Let's go to that. Yes. Let's go. Now, this is the displacement issue, which we've already talked about, but it gives you the formula. And here is your v of t is equal to t cubed minus 10t squared plus 29t minus 20. Okay. Well, I didn't open parentheses, so there's no reason to close one. Okay. Now, that's a continuous function, right? Now, we've already seen the graph, and pretend you did. Let's just say they gave you this from scratch. You know that's a continuous function, okay? And we're interested in it only from t equal 1 to 5. So we want to know total displacement. So we need to know absolute value. So we need to know when this is positive and negative. Okay, it's a polynomial function. Polynomial functions have two really important characteristics. They're smooth and they're continuous. Okay? Nice things to have. Okay? That means you don't have any sudden breaks in them. Okay? And you don't have any points or cusp or things that are irregular. They're smooth and continuous. So, that leads to another issue. If they're changing direction, which is the thing we are looking out for here, if you're doing total displacement, you need to know, total distance traveled, you need to know where you stop, back up, stop, go forward. You need to know that kind of stuff. Now, every time I say a stop there, what I'm talking about is a zero for the function. That's where the velocity is equal to zero. And the velocity is going to be positive on one side of that, negative on the other side, because there aren't any cusps. Now, the only other thing, if it came down and kissed the axis or came up and kissed the axis, yeah, you may have been, not a change of sign. So one thing we want to see is where the zeros of the function are. And then we'll evaluate whether it's going forward or backward, and then we can do the absolute value. We need to know where the function is positive and where it's negative. So to do that, we need to know the zeros. All right. That said, one way to tell the zeros of the function is you set it equal to 0. And then you see if you can factor. Now, what's the only technique we have so far in our belts to factor a 4-term polynomial? What's one technique? Grouping. Okay? If we tried to group these two terms and those two terms, the common factors here would be t squared times t minus 10. No common factor at all there. So grouping is not going to help us in this problem. Okay. For generic polynomials that you don't have that, the next thing we do is, does anyone recall? It was called the rational zeros test. Oh boy. How did that go? Well, here is a polynomial function. If we wanted to find its rational zeros, that always going to be of the form. Perfect attendance again today, folks. Last Wednesday was the only day so far this term that we didn't have perfect attendance. Way to go. Back on track again. Okay. So just talking about rational zeros test before the exciting news came in. All right. The rational zeros test said that for all the rational zeros here, they're going to be of the form, let's see, how did they express it? P over Q, I think, was what they usually did, wasn't it? P over Q, where P are all the possible factors of your constant term, and Q was all the possible factors of your leading coefficient. Hey, I can do the leading coefficient plus or minus 1. Okay, that's the only possible factorization of 1. So let's look at all the possible factorizations of 20. You tell me. All plus or minus 1, continue, plus or minus 2, continue, plus or minus, actually there's a 4, and plus or minus 5 you got, plus or minus what? 10, and finally 20. Those are all the possible factorizations of this rational zeros. Okay? Now, your denominator is 1. Okay? So in other words, your numerators are just those. But remember, we're only dealing with 1 through 5. That's the only time that we're interested in. So I don't care if there's a 10 or a 20 out there. I'm going to throw those away right now. Who cares? Okay? 10s and 20s aren't going to matter. Let's see about the other. Easiest one of these to do is 1. And the easy way to figure out whether 1 is a 0 or not, plug it in, plug it in. Okay? What would this be? 1 minus 10 plus 29 minus 20. What does that add to? There's a minus 30 and a plus 30. There's a 0. 1 is a 0. What do I do with that then? Good old synthetic division. Only I put a minus 1 here. Remember, you always do the opposite. No. You do a 1. Sorry. If it's a factor, you put the opposite. For a 0, you put the actual number. Okay, 1. Okay. Now, notice what else that gave me. These are just your coefficients here. 1, negative 10, 29, and 20. minus 20, okay? Three third-degree polynomial, you would have 4 terms. You're set up to go. Synthetic division right there. Y'all remember how to do synthetic division? Okay, we'll go over it right now. You write down your coefficients, and you write down what you think the zero will be, and we already know it's going to be 1. Okay? So here's what we do next. Skip a line, draw a line. That's my rule. I've never seen it in a book. Okay? Bring down the 1. And from this point on, you're multiplying and adding, multiplying, adding, multiplying, adding. So multiply 1 times 1 is 1. Add, negative 9. Multiply, negative 9. Add, 20. Multiply, 20. Add, 0. Ding, 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 ding. That means it's a 0 of the function. The remainder is 0. Well, we knew that. We had already plugged it in. But what we didn't know was what the quotient was. We know the divisor, we know the dividend, we didn't know, and we knew the remainder, 0. But we didn't know the quotient. Now we know the quotient. What is the quotient? You tell me. T squared minus 9t plus 20. See, what we did to get this, we just took the t's out of the problem. When we did our division here, synthetic division, this really stood for x minus 1 dividing into that. You know you're going to come up with, t minus 1. You're going to come up with a t squared with a remainder 0. And sure enough, that's your quotient. Now, we can continue with synthetic division, but why do it? We know what to do to factor this one. We couldn't factor that. We didn't have any tools to. So we did rational zeros test. Started there. Found out 1 worked. So did it with 1. Now we've got a quadratic. Can we factor that? Please say yes, okay? How does that factor? T times t. That's the only way you can get t squared. Then we look where? Sign of the last term is a positive. What does that tell you about these two signs? They've got to be the same, and you look up here to the middle term, that's negative. So they both got to be negative. And now you want two numbers that multiply to be 20 and add to be 9. 4 and 5. Look at that. Okay? Multiply to be 20. Check it. T times t is t squared, minus 5t, minus 4t is minus 9t, plus 20. Yes, yes, yes. So here are the other two factors. One factor was t minus 1. The other was t minus 4. And the other was t minus 5. There's the three factorizations, the three factors of that trinomial. And those are the only three. Because you can't have more zeros than you have your maximum maximum. We got them. We found them all. 10 and 20 would never have worked anyway, because that's all you got right there. So that tells you we have 3 zeros. T equal 1, well, that's one endpoint. You saw that on the graph. T equal 4, that's a point in between. T equal 5 is our other endpoint. So all we have to do is figure out where is this thing positive or negative. Well, let's pick a number in between 1 and 4. 2. Okay, let's plug it in. 2 cubed is 8. And 2 squared is? Second? 4. And minus 10 times 4 is minus 40. So 8 minus 40 is minus 32. Okay? And then 2 times 29 is? I almost said it. 58. And this was a minus 32. So now we're up plus 26 anyway, right? Something like that. Minus 20. It's positive. So guess what? We know between t equal 1 and t equal 4, that is always positive. Because these are our two zeros. If it's positive in between, it can't go negative in between. Otherwise, it can have another 0. So we know it's going to be positive there. And last check. I hate doing 4 1/2, but pull out your calculator, okay, and do a 4 1/2 and see what you get. 4.5 cubed, 4.5 cubed, minus 10 times 4.5 squared, plus 29 times 4.5 minus 20 equals. I guarantee you it's going to be negative.
Negative 7/8.
Yeah, it's negative, okay? Why could I guarantee that? Because we know it's a 0 here at t equal 1. We knew it's positive between 1 and 4. Because 4 is a multiplicity of 1, it had to cross there. Had to cross the x-axis there. For it to touch and go back up again, it had to be an even multiplicity. It didn't. That's exponent of 1 right there. So it had to cross. We knew that. I didn't have to have you check that. And then it comes back up at 5 there. So since we already showed it's positive here, it had to be negative down there. So we didn't really have to do it. Okay, so what does that mean? Now let's go back to our next thing. We know from 4 to 5 it's negative. Okay. All right. So what's the absolute value of v of t dt? That will be the integral from 1 to 4, because it's all positive there, of, oh boy, they don't write it down here. Remind me, t cubed, was it minus 20t squared? Yeah, minus 10t squared. Minus 10t squared plus 29t minus 20. Okay? And we do that from dt. Okay? That's where it's positive. And then we do plus, we do the absolute value of that, which means the opposite of that, because where it's negative, the absolute value, you just change the sign. Okay? So therefore, it'd be from 4 to 5, it's going to be minus t cubed plus 10t squared minus 29t, yuck, plus 20 dt. Because the absolute value of a negative number is the opposite of that number. And since we know these are negative down here, we do the opposite of that there. So let's do the math. Isn't that fun? Okay. What's the antiderivative of t cubed? T fourth over 4 minus, help me.
Minus 10t to the third over 3.
Over 3, perfect, plus 29t squared over 2 minus 20t, evaluated from 1 to 4. Okay? Now, if this is all right with you, I'm going to pull the minus sign out, okay, because we did a plus up here. But if we make this a minus here and go from 4 to 5, then this is going to be the same thing as what we had before. That just changes that to plus, this to minus, that to plus, and this to minus, right? If I pull the minus sign out, okay? So it's going to be the same thing. So I don't need to do this anymore. It's going to be t fourth over 4 minus 10 t cubed over 3 plus 29t squared over 2. Yeah, this drives me nuts. 2 over 2 minus 20t. But I'm going to have the minus in front, and this will be going from 4 to 5. Okay? So, unfortunately, there's no zeros here, so we're going to have to do all the evaluations. Okay. So plugging in a 4 here, 4 to the 4th power, anyone know that?
64?
No, 64.
Okay. It's a 4 squared would be 16 times 4. Oh, it's more than that. 4 cubed is 64. And then 4 times that is 128. Is that, no. 256. 256. So 256 over 4. We can divide one of those out. Minus 10 times 64 over 3 plus 29 times 16 over 2. That's pretty ugly, isn't it? Okay, minus 80. Can I do that one in my head? Okay. Now we got to do the minus of that with 1 plugged in there. So that's going to be minus 1/4. Minus a minus is going to be, oops, nope. Yeah. Minus minus will be plus 10 thirds. Okay. I'm going to, because it's getting in the way here, erase that. Okay. Still messy, but a little less messy. And then we got a minus 29 over 2 and a plus 20. Yeah. Okay. Whew. Now, we got to do the same thing, but this time plugging in a 5. But there's minus in front here, so that's going to be a minus 5 to the 4th power, 625? I believe that's right. So that's 625 over 4. Okay. Minus, oh wait, plus, minus a minus will make it a plus. 5 cubed is 125 times 10 is 1250 over 3. Minus a plus is going to be a minus 29 times 25 over 2. This is getting awfully ugly. Okay, let's get down to the next line. Plus 100. Okay, because it was minus a minus, which is plus 100. Whew. Now we do our 4 again. But it's now a minus, so that's going to be a plus 80, right? And guess what? No, it's not plus 80. It's plus, right, yeah, it's the same thing we had double. Okay, sorry. Okay. When we're doing a minus the 4, it's a minus, which is plus, and then it's going to that T4 over 4, which is the same as what we have here. So it's another 256 over 4, minus another, that's 640 over 3. Yuck! It's an ugly 640. The pen keeps messing up. Of course, the writer is no better. Okay. I can't do that one in my head. Another plus 29 times 16 over 2. Okay. And then another minus 80. All right. Okay. So you got all those numbers, you add them together. Boy, what a pain in the neck that is. Okay? And they just magically come up with an answer without showing you how they got it. And hopefully if you plugged all those things in, you would also come up with 71 over 6 feet, okay? Whereas before we got 32 over 3, which is a little more than 10 feet. This one will be a little more than 10 feet. Ooh. The other one was 10 2/3 feet. This will be, oh, yeah, it'll be 11, a little more than 11 feet. Okay, you're right. All right. So I'm not going to do all that. Hopefully you can. This simplifies pretty simply. I should have just written that. Better go on and simplify. That becomes 64, right? Oh, 4 times 64 is this. So this is 64, that's 64, that's 180. You can't divide anything in there. That's where, so leave that alone. But it'll be minus 1280 over 3. And then this will be 2 will go into 16, 8 times 29, whatever that is, and double that. Oh, that'll just be 8 times, 29 times 16, because you add the 2 together and you lose 1/2. Minus 160. And then you've got to do these, and then those, which include that. So you just got to do it and see what you get. And supposedly you get 71/6. That finished 4.4. I hope you didn't want me to show all those steps in math, did you? After that, it was just math, okay? Fractions, no less. So homework exercises, do either 7 or 5, okay? They're both at calcchat.com. Do any of the odds 9 to 35. They're all at calcchat, 19's at calcview. Do either 37 or 39 or both. They're both at calcchat, 37's at calcview. Do any of the odds 41 to 45. They're all at calcchat, 43's at calcview. Do any of the odds 47 to 51. They're all at calcchat, 47's at calcview. Do any of the odds 53 to 57. They're all at calcchat, 53's at calcview. Do any of the odds are either 59 or 63. They're both at calcchat. Do 63, it's at both at calcchat and calcview. Do 65, it's at calcchat alone. Then do 67, it's at calcchat alone. Then do any of the odds 69 to 73, they're all at calcchat, 71's at calcview. Do any of the odds 75 to 79, they're all at calcchat, 75's at calcview. Do any of the odds 81 to 85, they're all at calcchat. Do any of the odds 87 to 91, they're all at calcchat. Do any of the odds 93 to 97, they're all at calcchat, 93's at calcview. You can look at 99 and 101. If you want to do something with that, feel free. You don't have to. Do 103 if you can. That's a calcchat. It's very similar to the one we just did. Okay, so it's a good thing to do. And then there's the error analysis. I really don't like these problems because they're showing you something wrong, and you have to figure out why it's wrong. But I hate for you to be reading stuff that's wrong. So if you can handle that, do set 105 or 107. They should be at calcchat. There's a true-false 109 that should be at calcchat. Then there's a couple of 111 to 113. You can do either one of those if you want to. They're at calcchat. The Putnam Challenge, if you're interested in that, go for it, but you don't have to. And then there's a section project, and you don't have to do that either, but if you find it interesting, you can go for that. All right. That pretty much wraps up 4.4. Any questions? Oh, they also too can be. So here's what we did. We broke that just like they did, the velocity function into 2 pieces, 1 to 4 and 4 to 5. For the 1 to 4, we had this. And 4 to 5, since they pulled out the minus sign like I did, they have that same thing again. The only difference is it's got different limits. Now, they did the antiderivative and got exactly what you did. T fourth over 4 minus 10t cubed over 3 plus 29 halves t squared, or 29t squared over 2, minus 20t, minus the same thing. That is the same integrand, but these are evaluated from 1 to 4. Those are evaluated from 4 to 5. Okay. What you say again? Where did I get the t's from? That was your variable of integration. Okay. Starting over. The t function that they gave us at the very beginning was this thing right here.
Oh, they gave us this.
They gave that as the velocity function. And then that's what you're integrating. I see what you're asking now. Okay. And then when you plug in, they say you get this. Oh, yeah, I could do that in my head. Couldn't you? No, wait. Okay. That just sort of aggravates me how they do things like that. But let's see. There may have been a slightly easier way to do. This would be 4 to the 4th, which we know is 256 over 4. And if you do this one, there's just no way they can do it that quickly. I'm just not convinced they can. You know, that's a bit much. So you just have to plug it in, and you wind up getting something like that, which comes out being 71 over 6 feet, which we didn't do. We let them convince us it was it. Yeah, 71 over 6 feet. Okay. Which is something a little bit more than 11 feet. The other one's just a little bit more than 10 feet. So you do go further because it's not backtracking any. You're actually the distance traveled. Okay, that's the end of the section. Let's move on to 4.5, which is something we're going to be using repeatedly. This is probably one of the most common techniques we do for integration. It's not in the techniques chapter because I guess they count it too fundamental to do there. But boy, you use this a lot. Okay? I'm waiting for PowerPoint as usual. Okay. So let's go from current slide. All right. We're still in integration, chapter 4. Okay? We are now going to do integration by substitution, a very common technique used. We'll use a pattern recognition to find an indefinite integral. Okay? We'll use a change of variables to find an indefinite integral. All right? We'll use the general power rule for integration to find the indefinite integral. Okay? We'll use change of variables to evaluate a definite integral, and we'll evaluate a definite integral involving an even or odd function. All right, pattern recognition. I do this all the time, but I've never seen a book that had a section they call this, so this is sort of going to be interesting. Okay. In this section, you'll study the techniques for integrating composite functions. There is the key. These are functions that contain functions within the functions. The discussion is split into two parts, pattern recognition and change of variables. Both techniques involve a substitution by some other variable. And since our most favorite variables are usually x, y, t, those kinds of things, they let the substitute variable let u equal this. So that's why they call it a u substitution. That doesn't mean u substitution. Okay. With pattern recognition, you perform the substitution mentally, and with change of variables, you write the substitution steps. You know what? Generally, I think writing substitution steps is going to make more sense.
unless it's just patently obvious. The role of substitution and integration is comparable to the role of the chain rule in differentiation. So basically, we're kind of undoing the chain rule. There's the key. Okay. Now, here's for you to recall. For differentiable functions, if y is equal to capital F of u, but u is some g of x, then you can write that y is equal to g of f of g of x. That's chain rule. Then if you're taking the derivative of the chain rule, it's the derivative of the outer function times the inner function times the derivative. Evaluate at the inner function, then times the derivative of the inner function. So, from the definition of an antiderivative, it follows that if you had something you see is the derivative of a function of a different function, then times the derivative of that inner function, then you can say, oh, well, that's just f of g of x. Plus c, because integral you always have for indefinite of a constant at the end. Now, I think I know where they're heading, but rather than risk making a mistake, I always like to write down. Now, there are some things that are just sort of patently obvious that you might be able to just write it down, but most of the time, I'm going to make that use substitution. And I think they will too, but they just don't write it down, is what they're saying. These results are summarized in the following theorem: the antiderivative of a composite function. If g be a function whose range is an interval I, somewhere here in this interval, that's the range of I, meaning the g of x or g of t or g of whatever it is always going to be in that range I. Let's let f be a function that is continuous on that range I. The function f is continuous, but g has a range of that. If g is differentiable on its domain, which we haven't even mentioned yet, and f is the antiderivative of little f on I, then remember capital F is the antiderivative of little f. So that means if we take the derivative of little f, that is capital F. Okay? So the integral of f of g of x times g prime of x dx would be the antiderivative of this is capital F of g of x plus c. Okay. Frankly, at this point, even to me, I know what they're talking about, but it seems like a lot of blah, blah, blah. Okay? Once we get real numbers in here and functions that we can see, I think it'll make a lot more sense. So here's basically what they're saying. Let's let u be this g of x. This thing here, the innermost part here, whose derivative shows up there. Okay. Once you do that, then du is going to be g prime times dx. Okay? Now, what we have then is the integral of f of u, because u is g of x, times du, because du is g prime of x dx. And you know what this is? That's f evaluated at u. But what is u? G of x. So it's f of g of x plus c. It gives you exactly this. So rather than try to keep all that in your head, just do the substitution and it works. Okay? Now, example 1 is going to show how to apply that directly. Okay? And we're going to get to it in a minute. But notice that the composite function is in the integrand has an outside function f, inside function g. And moreover, the derivative of g prime, is present as a factor in the integrand. So the outside function is f, the inside function is the g, just like we talked about when they're composite functions. But then you also have the g prime there, so all you have to have is the antiderivative of this, and that's what gives it to you. Okay? But it's so much easier just to do it. So let's do example 1. Now, here's my little rule. Find the innermost part of the most complicated part of the integral. Of this integral, integral of x squared plus 1 squared times 2x dx. What seems to be the most complicated part of that? Yeah, it's this part right here. Okay? Then do the innermost part of that. That would just be the x squared plus 1. Just do the whole thing, x squared plus 1. And let that be your u. Okay? That's where I began. The innermost part of the most complicated looking part of the problem. And this is the most complicated part, so I've got to get my pen back. Okay? So let u equal x squared plus 1. Just that innermost part. Okay? That's all you worry about. And then the next sentence is always the same. Then du is equal to what? Write it in differential form. It's pretty easy. Take derivative of x squared. What do you get? 2x dx. Done! Right there. Okay? Now, take a look at what we got. The 2x dx, that's right there. Right? So there's du, and u was this part, so this becomes the integral, and the x squared plus 1 is u, and that u is squared, and then you got du. Don't you? And I think we all can do that one. What's the antiderivative of u squared du? Anybody? U 3 over 3. Okay, and it's an indefinite integral, so we put a plus c at the end. Okay, but we made up the u, so let's go back to the original problem, which was the x. What is your u? Okay, so this will be x squared plus 1 cubed over 3 plus c. That's it. Now, you can write that a couple of different ways. 1/3 x squared plus 1 cubed plus c. It doesn't matter how you write it, okay? Except if you're doing WebAssign, then they will only want it one way, and it's sort of a mystery to me how they choose their ways, but that either one of those two answers is perfectly fine. Don't forget your plus c's if it's an indefinite interval. And does that make sense? Well, if it didn't, what you could do is take the derivative of this and see if you get the integral here. Well, sure enough, the derivative of this would be 3 times 1/3, which is 1, times x squared plus 1 squared. Chain rule times 2x. And that's exactly what you got there. Oh, yeah, let's do it. Okay? Let's first see how they did theirs. Okay? Hopefully they didn't do too much very differently, but let's see how they did it. Letting g of x, okay, they went with the g of x. I far prefer u. G of x be x squared plus 1. Same deal. Then you find g prime, which is u prime, du, is equal to 2x dx. I like that far better than this way. Then f of g of x would be f of x squared plus 1, but the f function would be your squaring function, so that would be x squared plus 1 squared. From this, you can recognize that the integral follows that pattern. My goodness, isn't u much easier than this? And they make it seem like this is the easy way to go. To me, this is actually more confusing, sort of gobbledygooking it all up when you just let u be something, go for it. Okay, then they recognize that this is f of g of x and that's g prime of x, so then we can just put your thing, just put the u in there and it's so much easier. Okay, wow. Okay, but if you like it this way, it works.
I don't know what's wrong with your mind. No, I'm sorry, but yeah. And they wrote it with the 1/3 up front. It doesn't matter. 1/3 x squared plus 1 plus c. Make sense? All right. Now, do I like their pattern? Not particularly. I mean, it's all true. It certainly works. You just had to recognize the pattern, okay? You had to look in the crystal ball to see, oh, there it is, you know. Whereas if you let the U be there, it all comes out in the wash so easily. Now, it says you can extend this technique considerably with the constant multiple rule. In other words, if you had some constant in front, move it on the outside, okay? Even if you have to introduce the constant in front, move it on the outside. Many integrands contain the essential part, the variable part of your G prime, missing a constant multiple, put it in where necessary, okay? In such cases, you can multiply and divide by the necessary constant multiple, and we'll see that in example 3. But y'all wanted to do example 2 first, didn't you? So let's go back and do example 2. Okay, let's do example 2 here. Find this, the integral of 5 cosine 5x dx. Okay, now what's my little rule? First, find the most difficult part of the problem. And here we're dealing between 5 and cosine 5x. What do you reckon is more difficult? Cosine 5x. Let's go to the innermost part of that complicated part, and that would be the 5x. That's the innermost part. And guess what we're going to let that equal? U? Yes, U. U too? No, just U. So we'll just do U. Let U equal, what do we say? No. The innermost part. The innermost part. 5x. Okay. Then, and what do we always do next if we figured out what U is? Yeah, take a derivative. Du is equal to 5 dx, isn't it? Write it in differential form. You take the derivative of u as du, derivative of 5x is 5, and then times dx. Right? Okay. Now, we take a look up here, and we see, sure enough, there's a 5 dx right there. This is your du, and this will just be cosine of u. So our integral becomes the integral of cosine u du. That's it. That's it. Can you do that? Yes.
Do they always work out like this, where it's like this neat little...
No. Dream on. Slap yourself. Wake up. You're dreaming. Okay. No. And that's what we're going to see in the next example. Sometimes you have to modify a little bit. But usually it's pretty simple. Okay? These are just set up to be very easy. Okay? But can you do that integral? The antiderivative of cosine u. Sine u, you got it. That's equal to sine u, and because it's an indefinite integral, we have to put a plus c. Okay. Now, you're giving me an answer in u's, but the problem originated with x's. So let's plug in and see what that is. The sine of, and what was u? Dimitri. No, never mind. That's not what. DeMarcus, I'm sorry. 5x. Sine of 5x plus c. Now, I don't see how their pattern can be any simpler than that. Okay? actually the pattern to me gets more complicated. That's about as simple as you can go. Okay? And that is, by the way, let's check to make sure. Sine 5x plus c. Yes. Okay. Now, goodness, my stomach is growling like crazy. We already mentioned the constant multiple, and we're going to deal with that in a minute. Before we do that, let me write down a few of their recognition things. And this is worth recognizing, but I'm going to do it slightly differently. Here's an integral. The integral of 2x times x squared plus 1 to the 4th power dx. Rather than messing around with recognizing patterns, I would say the question, what's your u? X squared plus 1. The innermost part of the most complicated looking part. Yes. If you identify that u equal to x squared plus 1, what's your du then? U is equal to this. It's what?
X. I don't see how you be getting du. How do we get du? I see du.
All right. You said, if I was listening right, let u equal x squared plus 1, right? Now what I'm going to do is then take a derivative of u, du. But I'm going to do it in differential form. I could do du dx. Would that make it more sense to you? No. Okay. Taking derivative of x squared plus 1, what do you get? Wait, you're integrating. Take a derivative, yeah. That old stuff we used to do, yeah. Oh, you had to forget that. That was last term. I finished that course. I don't need to do that anymore. 2x, you got it. And then times dx. What we did before was say du dx is 2x. Writing it in differential forms, it's kind of like you multiply dx on both sides. That's in differential form.
Oh, so you just
Take the derivative of u, that's what du means, and it's like u dx over there. Huh? That du means take the derivative. Yeah. Okay. Let's do the B one here. The integral of 3x squared times the square root of x cubed plus 1, and outside that, dx. Rather than messing around with pattern, just ask the question, what's your u? Wait. Okay, no. Take the innermost part of the most complicated part of that. X cubed plus 1. Let that be your u. Let u equal x cubed plus 1. And what's your next line? Then du is equal to 3x squared dx. Got it. And then you see there's a 3x squared dx right there. Over here, here's a 2x dx right there. Okay? That's when life is beautiful, you know, and it all works out for you. Don't get used to it, okay? This is just setting you up, okay? Now, can I go on and erase those two? Need it a little longer? What's that? Oh, go on and finish these? Okay, just the second one. Okay, well, what would you tell me that would become then? The second one there. The 3x squared dx is going to be your du, right? So this part here is going to be your du, because that's what it is, right? Then what's the next part? What's that? Well, what you got left? Square root of x cubed plus 1. What's x cubed plus 1? It's u. It's u, bud. Yeah, okay. Right? So that would be, and I don't like to put square root in there, so I'm going to call that u to the 1/2. But you could put square root of u du. I'm just going to change that to u to the 1/2 du. Right? And we can do that antiderivative, can't we? Please say yes. What would it be? Okay, let's go back to the previous one. That would be the integral of the 2x dx is your du, and your x squared plus 1 is u, and that u was to the 4th power. And what would be that antiderivative? U to the 5th over 5. And that would be plus c. And then plug back in, and that would be x squared plus 1, that's your u, to the 5th over 5 plus c. Okay, you do the same thing here. How did you get that u to the 5th over 5? Yeah, you went up by 1, didn't you? Okay, but how did you do it? You went up by 1, right? Okay, well, here you do the same thing here. What is 1 plus 1/2? 1 plus 1/2. Three halves? Yes, that would be u to the 3/2. But then what did you do with that coefficient? Divided by it, right? Yes, that's it, exactly, 2/3. And then you put your plus c. Yeah, okay. Too crowded up there, huh? Okay. So, now just go back and put in what u is, or u are, okay? That would be 2/3. What's that? Yeah, when you take the antiderivative of u to some power, you just, and then after that, you plug it back in, and u was x cubed plus 1 to the 3/2 power plus c. That's it.
Something that I'm struggling with is why is it usually 1/2?
Oh, this was, okay, yeah, I skipped that step because I was running out of room. What we had, this part here was your du, right? Okay, this part here was the u, the square root of u. What is the square root of u? I don't integrate radical signs. I put them in exponential notation. What's that?
That's a 1 at the end, and then on the
It's the very bottom. Okay, right. Is there
Page 10.
Huh?
Page number 10.
on the lower right or bottom?
Far right. Oh, let's see. It just didn't come out. I think I got into the boundary there. You see, it doesn't write well over there. Yeah, it wasn't really a problem, but that would have been the answer had it been a problem. Okay. It was just sort of an example. They're just saying, recognize the pattern. And now, which to me was find the u. That to me is easier to do. So rather than recognize the pattern, I say find the u. Sort of like find Waldo. Where's Waldo? Okay, never mind. Y'all don't remember that, do you? Okay. Now, here's where we get in. Clark was really disappointed these were so simple. So he wanted them to be a little more complicated. Let's see if we can make them more complicated. Here's the integral of x times x squared plus 1 to the 4th power dx. That looks almost just like something we did before, but we're missing something. And what are we missing? Well, where would you begin? most important part. Where would you begin?
X squared plus 1.
Yes, let u equal that. Let u equal x squared plus 1. The innermost part, the most complicated part of the problem. X squared plus 1. And your next step is always, then, you tell me, du is equal to 2x dx. Uh-oh, Houston, we have a problem. What is that problem?
They don't match up.
We don't have a 2x dx, we have an x dx. Well, how can I make this an x dx? Divide by 2. But you have to divide that by 2 as well. Okay? So, these go away. Okay? So what we have now is the integral of, and here, this part here is now du over 2. So I'll put the du on the inside and put the 1/2 on the outside. That's your du over 2. And the rest of it is exactly the same. U to the 4th. Because the u was x squared plus 1, that to the 4th du. And that's the same integral we had before, isn't it? We didn't focus on it much, but we did go back and do a little bit. What would that give you? Don't forget the 1/2. Antiderivative of u to the 4th du. Second? U to the 5th over 5. Okay, and then you have a plus c. So this would be 1/10, and then plug in what u is, x squared plus 1 to the 5th plus c. What's that? Well, it's 1/2 times 1/5. And then the u to the 5th would be x squared plus 1 to the 5th plus c. Last time it came out 1/5, u x squared plus 1 to the 5th plus c. But this one, since we didn't have the 2 there, we had to do it. Divide out by 2. And the next two do almost the same thing. You want to do those? Okay. All right, to erase that, or are you still needing? Okay. This time, the integral is x squared times the square root of x cubed plus 1 dx. That's an x. Goodness, this is awful. Okay. Too much erased. Okay. All right. Now, where would you begin? That u equal what? X cubed plus 1. Okay, then du is equal to 2x squared dx, isn't it? Oh, 3x. I'm sorry. You're right. 3x squared. Yes, yes, yes. You're way ahead of me. Okay. I can't get my head to work or my pen to work. Okay, 3x squared dx. And then divide both sides by 3 so you can get the same thing up here. Okay? So then, since the x squared dx is your du over 3, this new integral will have a du out here, and you put the 1/3 on the outside of the integral. Huh? And u to the 1/2. You got it. U to the 1/2. Because it's the square root of u. And we already did that one, right? Remember how it worked? 1/3. What did that become? 2/3 u to the 3/2. I can't write. I can't get the pen to write. Okay. Plus c. Don't forget your plus c. So this becomes 2/9 u to the 3/2 plus c. And then just go back, plug in what u is, or u are. Okay? That would be 2/9. What? X to the cube plus 1 to the 3/2 plus c. You got it. Okay, now the only thing is, do you have to take it all the way back to radical form? We didn't last time, and I suggest you don't do it this time either. If you wanted to write the radical form, just remember that the 1/2 is square root, so that would be 2/9. This is really taking it further than I think it needs to be taken, but you could if you wanted to. That would be the square root of x cubed plus 1 cubed plus c, or the other way you could write it is 2/9 square root x cubed plus 1 in parentheses cubed. It doesn't matter where you put the cube, inside the radical or outside the radical. Either one works. But the 1/2 part is the square root part, and this is the exponent part. It can either be inside the radical exponent or the radical inside it. Doesn't matter, but there's no reason to go back and do it anyway. But if you did want to get it back in radical notation, that's what would happen. But it's not worth the effort.
You can always do it that way, though.
I think they leave it as a, although, yeah, they don't, you see, these aren't finished. They are just saying, find the pattern, which to me is find the U. And we're doing that, but then you say, can we go and finish? And I said, yeah, let's finish. Okay, now, oh, we didn't do the C on the first part, did we? We didn't, did we? Let's do this part. Okay. Okay. The C on the first part was the integral of secant squared x times tangent x plus 3 dx. Now, this one's sort of have to do maybe a little more thinking. My little rule that I had, almost taking away the thought, you just look for that and go. This one you probably have to do a little more thinking, okay? I know it hurts, but we can get over it, right? Okay. Now, it may not look like it, but this is the more complicated part of that. Okay? And here's why. What is the derivative of the tangent? That's where the rub is. Anyone remember what the derivative of the tangent is? Second? Second?
I was going to say sine, cosine, but then it's probably cosine.
That is what sine is. I mean, what tangent is. But I said, what's the derivative of tangent?
No.
No. Derivative of sine is cosine. Derivative of cosine is minus sine.
Oh, is it secant squared?
It is exactly secant squared. So therefore, this is the more complicated part, because if you let this part be your u, which is what I suggest you do, let u equal tangent x plus 3. Then, what did you just say the du was? Secant squared x dx.
Now this part right here is your du, and that part is your u. So we have the integral of u du. Just like we did before, way back. What's the antiderivative of u? Say again? I can't hear you. No. Yes, you do. Yes, it is. U squared over 2 plus c, right? Because it's indefinite. And what's u? Tan x plus 3 over 2. Oh, and that's squared plus c. Or 1/2 tan x plus 3 squared. I don't care how you write it. There it is. Okay? Now, one sort of perturbation of that one, and this is sort of doing it in the opposite direction. In fact, I think what I'll do here is erase that and that. I probably should erase it all. This is sort of going in the opposite direction of what we have been going, but it still is valid. Here, there's what we got. 2 secant squared x tan x plus 3. And guess what? What's your u? It's the tan x plus 3. But, oh wait, u equal tan x plus 3. Then du is equal to secant squared x. Guess what? That 2 is just in the way. But it's just a constant. Take it off of there and put it out there. Right? You can do that to any constant you want to. Before, we were dividing and doing that kind of stuff. Why mess with it? Just take it outside. Now we got exactly what we had before. Precisely what we had before, except the 2 out front. So this is going to be 2 times the integral of du, that's the secant squared x dx, u. And that comes out being 2 u squared over 2 plus c. Only difference is the 2 wipes out that 2, and you have tan x plus 3, was it? Yeah. Plus c. Yeah, it's squared. I'm sorry. I put parentheses in. I forgot the square. That's it. You got it. You got it knocked. Okay? See how that works? All right. And that led, those exercises then led to this part about the k and moving it in or out wherever it's helpful. And then let's do example 3. How would you begin? Let u equal, and what do you choose it to be? X squared plus 1. I like it a lot. Then what? Du is equal to 2x dx. Divide both sides by 2. That wipes out that one. What's that? Yeah. Just okay, so 1/2 out front. What's your new integral? U squared. Okay. Yeah. Oh, yeah. Okay. You're doing x squared plus 1. Let's just do x squared. See, this is now u, right? So it's u squared times x dx, which is 1/2, and the 1/2's out front. Du. You see? Okay.
So could you start with a part that's not the most complicated and still like if you just wanted to let, let your u equal to x, or like that.
Okay. That wouldn't do you any good. Then you'd have a problem looking just like this, only have u's rather than x's, and then you'd still have to do a substitution. Now, if what you're asking is, could your u be x squared? Yes, you can do that, and it will work, but it's a little more work. And I'm lazy enough, I don't want to do any more work. So the easiest thing is to let that innermost part be it. But letting u equal x squared, that will also work. But it's a little more work to get it to work out. Okay. Easiest thing, let it be that innermost part. Do you want to finish this one? U cubed over 3, don't forget your plus c, and that will be 1/6. Second, x squared plus 1 to the third power plus c. Perfect. Okay. Let's see how they do it. All right. I think I'm going to have to erase in order to read that stuff. Okay, just like we saw before, similar to example 1, except the integrand is missing factor of 2, so recognize that 2x is the derivative of that. You can let that be blah, blah, blah. Oh, yeah, I like writing it that way. It's fine. That's perfectly correct. Just a lot of extra work. So what we didn't show is that, except they're going back to the g of x. Why don't you just call it u? Let u be this, and then du is 2x dx, and 1/2 du would be x dx. That's what you have here. So, and it's certainly right to write it as 1/2 of 2x dx. That's the same as that. And now pull the 1/2 out front, and everything's hunky-dory again. And that would be, and they go back to the F's and G's, which to me, they're absolutely, I know they're absolutely correct, but why not leave it as U's and U primes and stuff? Why go to this, okay? That to me is harder to see. I don't know, maybe it's just me. But the U and DUs, they make perfect sense to me, okay? And ultimately they get the same answer. 1/6, x squared plus 1 cubed plus c. Same thing as we got. But I can't remember if it was an English teacher in high school. She said, you're going around the elbow to get to your ear. You know, why do that? Why go all that distance? Go straight for the ear, okay? All right. Now, that was example 3. They call it multiplying and dividing by a constant. Perfectly fine. What's that? I still couldn't hear.
You were saying you had 8 minutes.
One more time.
He was saying you had 8 minutes.
8 minutes. Oh, wow. Okay. They have something at the bottom of page 298 I really don't like. They have what you can't do is take your x outside the radical. All you can take outside the radical is a constant. 1/2, 2, 17, 4/3 pi, any number, but you can't take a variable outside. So why they even brought it up, I don't know. So we're moving on to 299. Change of variables for indefinite integrals, which is what we've been doing, okay? Nothing new here, folks. We went right for the u's, you know. They kept it g of x's and g prime of x's and stuff. We've been doing this. Everything on here is what we've been doing, I think. Y'all see anything different? Okay. So let's do this one. Where would you start this problem? All right. Can I help you?
When do you not have class?
Okay, we're out of this class in what, about 5 minutes?
7.
7 minutes.
You mind if I sit down?
What's that?
You mind if I sit down?
Oh, please do. Okay, no extra charge though. You don't have to pay for it. Okay, all right, good deal. Okay, where do we go here? Oh, excellent. I like it. Let u equal to x minus 1. The most difficult part of the innermost part, the most difficult part of the problem. Okay? Then, it's always the next thing we did. Du is equal to 2 dx. You got it. Yeah, because you don't have a 2 up there, so let's divide both sides by 2, and we have dx. So dx is du over 2, so I'm going to pull the 2 on the outside, and we'll have the integral, and there's the du, and it'll be u to the 1/2 power. You're on top of this. So it'll be 1/2, and what's the antiderivative of u to the 1/2? 2/3 u to the 3/2 power. Perfect. Okay, oh yeah, plus c. Okay, forgot my last part. So this would then be another way to write this is this 2 and that 2 divide out, and that leaves 1/3 u to the 3/2 plus c. So now we do what? Plug it in. That would be 2x minus 1 to the 3/2 power plus c. All right, that's our answer. Want to see how they did it? Happy with what I've done? And you don't believe me, huh? Okay, let's see. All right, first let u be the innermost function, which is the 2x minus 1, just like you did, okay? To calculate the differential du, that would be du is equal to 2 dx, just like you did. But we don't want that 2 with dx, because you didn't have a 2 with the dx, so let's divide out the 2. And there they have dx is equal to du over 2, and the square root of 2x minus 1 is the square root of u. So you put that in there, and this thing that we had up here becomes this with that in there, but that's not what we wanted. They put it there. I take it outside to begin with. They bring it outside now, and now they take the integral of u to the 1/2 du, and that's u to the 3/2 over 3/2, which is the same as 2/3. But then, okay, and then they magically come up with this. The 2's divide out, and 1/3 u to the 3/2 plus c, which is 1/3 2x minus 1 to the 3/2 power plus c. Exactly what you got before, right? Doing all right, huh? Okay. Now, how's our time? 3 minutes. Let's go over, see where we are. Actually, the next thing coming up is example 5 that they don't do. Do you think we have time for it? 3 minutes. Well, that's the question. Can we do that one in 3 minutes? Right now, I would probably say no. But I think what we can do in 3 minutes is me give you some homework exercises. Don't you think that would even be better? Yes, of course. So let me put this in its place. We'll start with example 5 next time. It's not on the slide set. Then we'll do example 6, who's not on the slide set. But let's go on to the end of this section, which is a long section, by the way, fairly long. You can do any of the odds, either 5 or 7 or both. They're both at Calc Chat, 5's at Calc View. Then do any of the odds 9 through 29. They're all at Calc Chat, 15's at Calc View. And then they throw in a differential equation, which which just comes out of the blue. And so try to do those. If you can't, ask in class and we'll do those. They're both at Calc Chat, or look them up on Calc Chat. 31's at Calc View. And then the slope field. My word, there's nothing in the text like that. It's okay, but it's bizarre. So if you can't do it and can't understand it at Calc Chat, then we'll do it in class. Then there's another differential equation they don't have. And these are really easy. Try 37 if you can't. We'll do it in class. I think you can do some of the odds 39 to 47. They're all at Calc Chat. 45 is at Calc View. This guy is usually a lot more organized than this. I just can't see why. But this is something that he tends to do in other texts. He'll introduce a new concept in the exercise. You haven't done anything like it in the chapter, but do it here. Let's just stop somewhere there, and we'll pick up the rest of those later. Okay? Good deal. We probably ran out of time anyway, didn't we? Okay. That's a good place to stop then. So we'll pick up with example 5, which is not on the slide set, so remind me of that next time. But it is at larsoncalculus.com, so you can go back and look at it there.